about talking related to the stability. And stability, basically, here is the first case about the expression graphically of the characteristic roots onto the complex plane. So this section is regarding the stability. And so, for example, we consider the system like that one, and we always can express the characteristic roots in terms of zeta and omega n like this. X double dot plus 2 zeta omega n, x dot plus omega n squared, x equal to 0. So the roots equal to minus zeta omega n plus here we for case 1, zeta is less than 1, greater than 0. Okay, so case 1. So the root is like this. Okay. So the case 2 is zeta equal to 1, then the characteristic roots are simply equal to then that means x double dot plus 2 omega n x dot plus omega n squared x equal to 0. So the roots are minus omega n minus omega n. Case 3, zeta is greater than 1, so x double dot plus, and let me make out one example here and say the a x dot plus bx let me make one example. Okay, so for example, this is say 3. Okay, so the root or say minus corresponding to this one, whatever. Let me call the okay, something like this one. Alpha, beta are different. So graphical representations of the result is this. So this is the complex plane. And complex plane always have the real, we represent the real numbers onto the horizontal axis. Imaginary numbers onto the real, vertical axis. So for case 1, this is a real number, negative. So we put here minus zeta omega n. And for case 1, this is imaginary numbers. Imaginary number that is complex conjugate. So let me put here. So that is omega n, 1 minus zeta squared. And this is the minus omega n, 1 minus zeta squared. So the roots corresponding to this one, let me use this one, corresponding drawing is here and here. I use x as the mark to for the location of the roots. Okay. For case 2, and both are real. So for example, let me say that is here, that is minus omega n. So for case 2, the location of the root is here. They simply locate at the same locations, so 2x marks. For the third one, if you calculate, this should be, we can calculate this one. Minus 2a, 2a minus b plus b squared minus 4. Okay, so for this one, if you're going to calculate for the one, and one should be here, and one should be here. Okay, so for case 3, let me use the colors. One should be here, one should be here. So that's a graphical representation. As long as you are able to calculate the characteristic roots, you can always label there. And for all the systems here, we explain are stable. We call it a stable system. What is stable systems? If you remember, for case 1, our response is something like this. It's going to decay to 0. And for case 2, our response is something like this, if you remember that curve. For case 3, we have the response something like this, right? So that is the response corresponding to the vibration system we've been dealing with. Either case, you can see the response eventually going to 0. So if the response x of t, the magnitude doesn't explode it's going to converge, then we call the system called a stable system. Okay, so on the other side, what is called an unstable system? Unstable system, that is the response exploded. What kind of exploded? For example, if the response is something like this, getting larger and larger until the components break down. Okay, or without any oscillation, if the response is something like this. Be good? Any unstable system corresponding is this. As long as once you calculate the characteristic root, if the root has the positive real number, that means as long as you find if your characteristic root locating on the right-hand side of the complex plane, then that's the unstable system. Unstable regions.